I know.
Okay, so you got your test back, so we can talk about them a little bit, but I don't want to spend a lot of time on it. Got several other things I need to do today. But I usually will go through and answer any burning questions that you have, but also try to get some of the ones that were commonly missed. Overall, though, the class average was much better this time than last time, so there weren't any that were just completely across the board commonly missed.
What was the average?
Average was right at 86. Median was 86. I'm not sure what the mean was, but right around there. Probably the most commonly missed were the adjusted means on the very last page. That one, there were at least half of the people that didn't get the right parameter estimate in that. All right. Does anybody want me to talk about one before there? I did want to mention the very first problem. Somebody told me a long time ago, one of those education researcher type people, that it's been shown, and as a statistician I say this a lot, research has shown that if the first question on a test is easy, then it kind of relaxes people and they do better overall on the whole test. So I always try to, but on this one I caught several of you on that first problem. I thought I was giving, they'll be able to get this, and this is easy, right? But it says company makes dog food, blah blah blah, intended to aid in weight loss. They conduct a study. They have a new food formula. They want to compare to the regular diet formula, and they included equal numbers of small breed, medium breed, large breed, as breed size differences were also to be investigated. And then it says the response variable, the variable measured was the percent change in body weight after 3 months on the assigned diet. All right, so by now, if you missed it, I've circled the right answer. So the right answer is C, the two factors being studied. So what does that word factor mean? I think that's where people got.
Two explanatory, or I always think
Right.
explanatory proofs.
So in an ANOVA setting, the explanatory variables are called factors, right? So in ANOVA, explanatory are factors. So the people that missed this problem talked about percent body change, but that's not an X variable, explanatory variable, that's the Y variable, that's the response variable. So the two factors are the diet formula, the new one versus the old one, and what breed of dog they are, small, medium, large. Right? Everybody understand that? Okay.
Just on 4, I mean, I got it right, but can you do a quick explanation why it ends up tripling, like the number of comparisons, why it, if you have like if you use 0.5 alpha for the group comparisons, you end up with basically getting 15% error, like, does that make sense what I'm asking?
Yes. So the Bonferroni method. Bonferroni method is what you're asking about. You divide alpha by k, where k is the number of comparisons that you're making, right? So later on in the test, you did one with k equal 3, so alpha over 3, if alpha is 0.05, would be 0.0166 repeating, right? So your question is, why is it that when you do 3 comparisons, well, let me start this sentence over. Right? There were several people that missed this, and the common mistake, or the commonly missed answer that I got, I said, explain why this is necessary, and people said, oh, you do it to adjust the alpha level. But that, it says that right up in there, right? You're doing it to adjust the alpha level. So that's not the answer. But why do you need to adjust the alpha level, right? And the reason is because your type 1 error is inflated. Type 1 error is, and I'll put it in quotes, inflated, right? Because now you're doing 3 comparisons, and each of those comparisons has a 0.05 type 1 error. Remember, type 1 error is the probability that if the null is true, you still reject it, right? So you get data that makes it look like there's a difference when there's really not. That's called a type 1 error, right? Well, if you do 3 comparisons, each has a 0.05 chance of making that error, then your probability of making at least one type 1 error among the 3 is far higher than 0.05. It's not 0.15. It's not additive, right? And I didn't derive for you, but this kind of assumes it is, right? But I mentioned it at the time, but the Bonferroni method actually is an overcorrection. This is what it would be if those 3 tests were completely independent.
Yeah, you did say it was overcorrection.
Right. But they're not completely independent. If you're doing 3 multiple comparisons, like you have the one problem that we had 3 levels of whatever factor, and we did all the pairwise comparisons, right? Well, if you compare level A versus level B, and then you compare A versus C, these 2 comparisons are not independent comparisons. Why not?
Because you're having A.
Because A is in both of them, right? If A is dramatically different than B, it might be because A is just weird, right? So it's still going to be weird down here. So they're not independent comparisons. If they were all completely independent, then this would be the correct adjustment. But it's never, almost never, true that you have completely independent, because it's the same data set. You're using the same error term off of the ANOVA and all that stuff. So it isn't just that it multiplies out to 0.15. So I'm going a long way around to answer your question of why does dividing by 3 work? It actually doesn't work. It's an overcorrection. Right? You can derive what the correct...
Yeah, I said the other method though, but it's longer and more complicated.
Right. You could derive what it would be, but in order to do that, you would have to know, well, what is the correlation? You would have to somehow estimate the correlation between this test statistic and this test statistic, and then adjust for that correlation when you decide what to divide by. And that is a tricky, tricky thing. There are, I don't know how many publications in statistical journals on this topic of multiple comparisons adjustments, because it's tricky and it's approximate and it opens the door for lots and lots of... I've got a paper published in this area, so... Yep.
Number 9A, we did, I guess, the exact same thing. We don't know what we did was wrong.
Say it again.
9A.
9A. What's the matter with 9A? You said...
We both used a half, and you used -1 or 1. He used -1/2. I used a half, and I put the minus out in the 1.
Uh-huh.
I used 1 and 2 halves.
And you're asking why it's not that?
Why it's not that?
Okay. Let me just get another page. He's asking about number 9, and this one, that actually, I'm glad you asked that one, because that one was fairly commonly missed. On 9A, it says, just the scenario of this problem, you have 3 treatment groups: control, formula A, and formula B, right? So I'll label those as control, A, and B, right? And it says then, before collecting the data, one of the primary questions was whether formula B was significantly different than the control group. So we want to compare control to B. We don't want anything about A, right? And so the contrast, the population contrast, uses Greek letters. So that's psi equal. Now if I label this as 1, 2, and 3, which is the order they're listed in that little table, then this is A1 mu1 plus A2 mu2 plus A3 mu3, right? So 2, I don't want in there at all. So what do? 0. So A2 is a 0. You wouldn't even need to write it, but just for completeness. And then if I want to compare this one to this one, I just want the difference between them. So I want, you can use a positive 1 and a negative 1, or you can use a negative 1 and a positive 1. It doesn't matter. You just are doing the subtraction in the other direction. Right? So then this one, if I do negative 1 mu 1 and then positive 1 mu 3, you wouldn't need to even write the ones. Now, did you have a 0 in there, or did you have the other?
I had, I was not, I did the comparison, all 3 of them. I knew I was supposed to take one out, and I forgot to take one out, so I had it as -1 and a half and a half.
Okay. And so, and there were at least, you did the same thing?
I did.
I was saying, there's at least 2 people that did.
I did 0.5 and negative 0.5. I forgot to divide.
But you had a
the
0?
answer by 2. Yeah.
No.
I
Okay.
had the same thing.
So,
You had 0?
Yeah.
you had,
I mean, I
so there
didn't
were several
include
people that had
that. I just
basically
had
this.
it.
1 and then -1/2 and -1/2. What is that the contrast for? What are you
You're
comparing?
contrasting
The
all of
average of
them.
A and B, or the, yeah.
That's right. You're checking the control group. Is it different than the average of A and B? That's what this is checking.
Yep.
Right? If you did this, which is what Jeremy's saying he did, and Nate did that also. What are you comparing there?
The average of each, or
Average of the control.
yeah.
Or, hold on.
What do you mean the average of the control? Mu is the average of the control. You're taking half the average of the control and comparing it to half the average of the.
Okay, so
Right.
you divide. You have to.
They add to 1. It's a valid contrast.
I
did
did
not
the-
add to 1. They add to 0. So it's a valid contrast.
I did the opposite of the first one.
That's fine.
Yeah.
But there's nothing wrong with this. Your standard error will correct this. Right? The standard error has the squares of these coefficients in it, right? So you'll end up with exactly the same test statistic t and the same p-value. So just to answer the question, are they different, you'll make the right conclusion. It's just the number that you get back after you do it will be half of what the true difference is. Right? If I want to know, is there a difference between the mean for the control group and the mean of the B group, I can just subtract the means and say, well, the difference is about 0.04. Looking at it, well, it's about 0.035, right? But this will give you half of that number. It'll give you half of 0.035. So you couldn't answer, with this, you couldn't really answer what's the difference between these 2 groups. You could answer, what's half the difference between these 2 groups? See? There was some confusion about how to get the standard error for a contrast. Everybody had something that was almost right, but the wrong thing in there at different places. But the standard error for a contrast, just in general, standard error of a contrast is SP times the square root of the sum of the AI's squared over NI. Right? And what is SP? Square root of MSE. And the MSE is in the thing, in the ANOVA table above that. I remember there were a couple of people, don't remember who, but stuck in 0.01179 here. They grabbed the mean square for the factor instead of the mean square for here. There was somebody else that forgot to put the square root over it. Little mistakes like that. Is that you? You smiled when I said that.
Oh, no.
Okay. But root mean squared error goes out front, and then just each of the coefficients squared. Now it's easy here because if you have the right coefficients, they're 1s and -1s. So when you square them, they're still 1. Oh, so it's 1 over all of them have 40 for sample size, so it's 1 over 40 plus 1 over 40 square root, and then times the root mean squared here. So the answer should have been 0.01122. And then you form your test statistic by taking the sample value of the contrast, divide by the standard error, that gives you a test statistic, and it was statistically significant, even after adjusting for the Monferroni. Okay, let me look at number 13, and then we'll call it good on the exam. Number 13 was the one about adjusted means. So the first, let's see, part A, this is one of the ones where I deleted a question. My key has the old questions. Yeah, so I deleted part A. Part A was do the eyeball test and see if you think there's a difference. But if you do the eyeball test, you see that the difference in mean cases is 38, 36, and then 27. So one of them looks to be quite a bit different than the other. So just eyeball test, yeah, it looks like there's probably a difference going on there. But your part A is how to test for equal slopes. How do you test for equal slopes?
What problem
What
is
problem are
this?
you on?
It's 11.
Oh yeah, I deleted two questions. On mine it says 13.
Okay.
So number 11.
I was looking everywhere, and I'm like, there's
Sorry.
no-
Number 11.
You can use graphs. Like look at the.
Yeah, you could look at graphs, and you could do the eyeball test from those graphs. But if you want a formal statistical test, how do you test for?
The interaction.
It's the interaction. So equal slopes. Test with interaction of the covariate. In this case, that's last, the variable last. Covariate with,
Type.
yeah, type. The generic term is factor, right? Covariate with the ANOVA factor. Okay. Then part B was just look at the p-value for type in the model that has adjusted for covariate, and it was significant. But then to do the adjusted means, remember the formula for adjusted means is y bar for the, I'm going to say y bar 2 for type 2. So, and then I'll put little a, d, g, or j. Yeah, I like that better. So, my notation here is y bar sub 2 adjusted. So this is the adjusted mean for group 2. Got it? Type 2. And that's the unadjusted mean minus the slope across the covariance times the covariate means that you're adjusting for. Right? So the y variable mean for that group minus an adjustment for the covariate mean of that group. So there were people that got their y's and x's flipped around, but the most common mistake was getting the wrong value in there. That is the coefficient of the covariate term, the way it's written into here. That's the coefficient of the covariate term. So you find the covariate in your model output. It says last, down there at the bottom section where it says parameter estimates. So the slope is 0.89856. 0.89856. And now I'm just filling in values of the means, reading from the table, two tables up at the top. So the covariate mean for the second group is the variable last, and its mean is 26.4. And then the grand mean, that's what the dot indicates. The grand mean is, for the variable last, is 25. Okay? So now the only thing left is the unadjusted mean of the y variable. The y variable is the number of cases, and the unadjusted mean was 36. So when you multiply all that out, you get 34.742. Ugly 3. Okay? Now does that number make sense?
Yeah.
Before adjustment, the average number of cases sold was 36. Why would it go down?
To account for them selling a lot previously.
To account for the fact that they sold more the last period than the other types. They were more than the overall mean sold in the last period. So this, whatever store it was that got to use type 2, they should be sort of penalized for the fact that, well, you sell a lot anyway, right? So you need to subtract some off. So that's the adjustment. Questions? All right. So let's finish up logistic regression. And to do that, I want to go to the example we were looking at the end of class last time and finish this up. But I want to go through this using SAS and actually do it using the SAS Enterprise Guide, which is how you guys will work this stuff. Okay? So I have the output here on the screen, but this is in SAS, not Enterprise Guide. So I'll leave this there in case the other fails on me and I have to come back to this. But so let me get Enterprise Guide launched. And then we'll load the data. There it comes. I really need to remember to come in here with my own laptop and figure out how to hook it up to this thing. Because it's frustrating when you're standing here trying to teach and you click and you have to wait a whole minute before something happens. Because I don't have enough jokes to keep you occupied. Alright, so I'm going to open a new project and I want to read in the data. Now this particular data is already a SAS format file. Right? So all I got to do is read that in. If it was an Excel spreadsheet, then I would do File and Import Data, and it's pretty easy to get that. But if it's already a SAS data set, you can go to Tasks, then Data, and then Append Table. And then, let's see, I want to go up from that here. And must be 7th edition. Yeah, there it is. And so it's CS Data High GPA. That's the name of it. Okay, so this pops up. It says, oh, I found that data set you were looking for. And then I think if you just hit run, you accept all the defaults. That's fine. So if it was an Excel spreadsheet, you'd have a couple more of choices you'd have to make before it would load. Okay, so here's my data. Right? So I have GPA, But then I created already, but this variable high GPA, and it's a yes/no variable, ones and zeros. Right? So a high GPA is a 3.32, a low GPA a 2.26, and so on. So I think it's above 3.5 is considered high.
Be above 3.
Yeah, it must be a 3 because here's a 3.18. So I think it's above 3 is considered a high GPA. Below 3 is not high GPA.
Being awfully generous.
Yeah. So then we have high school math, high school science, high school English, SAT math, SAT verbal, and then sex. Right? And this data set has been sorted, so all of the ones are at the top, but there's zeros in here too. Okay? So, somebody venture an idea, where would I go if I wanted to do a logistic regression and try to predict high GPA? Okay, yeah, pretty much. Once you have the data in, and you're ready to start looking at the data, you go to tasks. I got to do a task. So tasks, and then regression, and then logistic regression. Yep, it's pretty simple, and it from there on, it's pretty similar to when you did regular linear regression. It does, though, allow classification variables. So I guess it's more like that general linear model that we did the analysis of covariance in. Right? So you can have classification variables. Those are your categorical grouping variables. So gender would be that, but since we have it 0 and 1, the interpretation of the parameter estimates is easier if you treat them as numeric variables. 0, 1 numeric variables rather than class variables. So I'm going to do it that way. So I'm going to take this high GPA and I'm going to move it into the dependent variable. Okay? And then let's just do the 3 high school scores to start off with. So actually I can just drag. I want to do that as a quantitative variable. Right, so I have my 3 quantitative variables in there, and I'm done. That's the model I want. So if you look over here, you can go down through all these different options on how to set the model. But if I click on model, the word response is the first subcategory that pops up, and it says response type. And the default is binary, which is what we have. Binary means it has 2 levels. If you click the down arrow, you can see nothing.
You have to leave logic regression.
Oh, is that what's popped up? Okay. So if it's binary, you get logit, probit, or complementary log-log. So the other 2 we're not ever going to talk about, so you know you're going to use logit, right? So we're going to click logit. That's not working right. It should give me other choices than binary. I guess not. So that's the difference between the enterprise guide and SAS, writing SAS code right in SAS, because you have other options. But here it only has one option. Yep.
Is it because you only have like the 0 and 1 things though?
That's a good thought. It may be because it already has recognized, hey, you only got 2 levels, so because the other one is multinomial. It will allow you, which means maybe you have like binomial, but you've got 3 instead of 2 or whatever. So maybe it's you might be right that it's already looked at the data for me and it's decided you don't have any other choices. So then down here it says fit model to level. What is it asking there? Fit model to level.
Your standard group or your control group.
See, I'm still in the response variable part of this. So fit model to level. You have 2 levels of response.
You want it to fit to yes or no?
You want it to fit. Do you want to model the probability of having a low GPA, or do you want to model the probability of having a high GPA? That's what it's asking. and we want to do high GPA. Not that it matters a whole lot. The mathematics works the same, but it's a little bit easier interpretation if you model a yes instead of a no. I must have hit the screen wrong. There. So remember last time I was showing you the code, and I said add the word descending, and that's what that's doing. Okay, so now I'm ready to go to effects. So I only put 3 variables over into dependent variables, so those are my choices here. I want to highlight them all. I can't do it with my finger, but I can do it with my mouse and the control button. I can highlight all 3 at once and then ask for the main effects of those. Alright, so I highlighted all 3, clicked on main, or I could have done them one at a time. HSE, main. HSS, main. So I have the main effects over here. Now if I want interaction terms, guess what that's called? Cross. Because it's like this times that, so it's a cross product. Right, so if I do cross, then it just put the 3-way interaction between all 3 of them. Right, so degrees, factorial degrees 3, if I make that, oh, I'm trying to go up. So I make it a 2, and then hit factorial, guess what it does?
It's gonna multiply all of them.
It puts in all of the 2-way interactions. So it was a 3 by default, so it gave me the 3-way interaction when I hit cross. If I hit factorial, there's my 2-way interactions. If I wanted, we won't even talk about it in this class, but polynomial degree 2, it would put the squares of those things in there. So you fit a quadratic model instead of a linear model. We won't do any of that. And we're not interested, we won't be doing in logistic regression anything with interactions, at least for now. But a 3-way interaction is incredibly difficult to interpret. Basically, it's, let's start with a 2-way interaction. You know how to interpret that, right? The effect of, like this bottom, HSS by HSM. So high school math, high school science. So the effect of high school science depends on their high school math score. That would be a 2-way interaction. Those that did terrible in high school math, then their science score doesn't seem to matter. But if they did good in math, then their science score is a good predictor. That would be an interaction. So how do you interpret a 3-way interaction? Well, it's the same argument, only instead of the effect of, it's the interaction between math and science changes depending on what they got in English. So the interaction changes. I don't know how to interpret that. So
And you could say that anyway, can't you?
yeah. Yeah, you can reverse the way that you say that. But I'm going to take all those back out because we're not interested in interaction. So down here's a remove effects button. So you highlight it and remove. So I'm just going to fit the 3 main effects. And then selection criteria. Remember when we did multiple regression? And we talked about some different ways of selecting what model or what variables go into the model. And in this class we don't talk about it much, but in regression class in the fall, we'll worry about these different selection procedures. For now, we're just going to put them all in there. And the only thing we looked at before was the R-squared criteria. Did R-squared go up enough to warrant putting that variable in the model? So we'll kind of do the same thing here, but we're just, the default is full model fitting, no selection. So you highlighted 3 variables, I'm going to put all 3 in the model. So then let's see what it says under options. So I clicked on options under model, and it's saying these are all things that you could ask for that aren't going to be given by default. Anything that's pre-checked is by default, and really nothing is. But correlation matrix of the estimates, covariance, influence statistics, all these things, this is assessing the model fit. This class doesn't get into that kind of thing, so you won't need to worry about them. If you want confidence limits on your parameters, Okay, parameters, what? What are parameters? The betas? So the slopes across those three variables, if I want confidence interval on those slopes, then I would put a check in one of those two. It gives you two choices on method to use. And you know, I'm not going to explain what walled is or what profile likelihood is, but everything by default is walled. So if I click in walled, it'll give me those confidence. Walled is some guy's name, and it's based on a chi-square distribution. So we over here call the walled chi-square. Conditional odds ratios, if you want conditional, then you need to have interaction terms in there, so I'm not going to ask for those. And then plots. If I click on plots, by default, it's checked show plots for regression analysis, all appropriate plots for the current data selection. Well, the default, when I ran it earlier, it's a ton of plots. And even I look at some of them and go, I don't know what that's trying to show me. You know, so you can decide what to do there. Remember that in logistic regression, we don't have residuals. So the old friend residual plot is not going to be there. So they do plots of these other model assessment statistics that they compute. It's not really that much use. I'll go ahead and leave it checked, but probably if you want to limit your output, just uncheck the plots and go on. And then I do want predictions. So I'm going to click on predictions, and I want to predict original sample, and we're not going to bother with prediction limits like we did for multiple regression. Right now, I just want to look at predicted values so you can see how those work.
So does that just add a column with your y hat or whatever the predicted? Teaching
Yeah,
your observation.
pretty much. But right here, you see that it says save output data, and that was grayed out until I said to do some predictions, and then it popped up, and it says local work dot. This is telling me the name of the data set it's going to put that in. It's not my original data set. It's not appending a column to that. It's making a whole new data set. But it'll have all of my original variables in it, plus these predicted values. Right? I can click on browse if I want to change the name of it or the location of where it's stored. Work, have we talked about the work directory? That means the memory of the computer. Right? So it's just storing it into RAM. If you want a permanent copy of it, then you have to define a library and all that. So don't worry about that.
So it still gives you the option for residuals?
Yeah, there's still
Or
there
it's
is
just
sort
for
of
prediction?
there's a residual for predicted probability, but it's not the same kind of residual you're used to. Actually, I'm going to put a check in and see what it does. Enables you to include additional statistics. Oh, that's generic. So we'll run this now, because the only thing left is, do I want to add some titles to my output? I can say, this is the analysis for exercise number whatever in the book. And then, I don't know what properties is. Don't need to, so run that. So this is, until it gets finished running, it pops up this log summary, and it's showing the SAS code that will do everything you just told it to do. And then it'll have notes and error messages in there if something was wrong. Notes are good, notes are in green, and errors are in red, so you don't want to see red when you go look at your log window. So here is the output. Okay, so let's start working our way down through this output. We had more variables in the model last time when we were looking at it, but we talked about the top part of this, right? We had a global null hypothesis. What is that testing? Do you remember? Testing global null hypothesis beta equals 0. What is that testing?
In other words, they don't predict.
It's all three. I have three variables, x variables in the model. And it's saying It's the old, all of those are zero. All of their slopes are zero versus at least one of them is not zero. Right? So this says, the null says none of the variables are good predictors. The alternative, at least one of them is a good predictor. And then, so we're rejecting that hypothesis. So we know at least one of those three variables is a good predictor of having a high GPA. Then the parameter estimates, we have an intercept term, and then these are the slope coefficients. After we do the logit transformation, the log odds, then this is just a regression. All right, so these are slopes. So for a 1 unit increase in high school English grade, it was on a 10-point scale if I remember right, a 1 unit increase would mean a 0.0361 increase in the log odds of having a high GPA. That's kind of hard to interpret. It's not your GPA will go up by that much. It's your odds of having a high GPA, logged, goes up by that much. So it doesn't mean a whole lot to me. But I can convert those parameter estimates into odds ratios by doing what? How do you get from 0.0361 to 1037? What'd you say, Emily? No? We did some stuff with reciprocals of odds ratios, but
You take e to the power.
e to the power of that parameter estimate. So do it on your calculator real quick if you got it handy. Take e to the 0.0361, and you should get 1.037. Right? Now interpret that for me.
So the odds of what are we doing high school English? So the odds of high school
Yes.
English are 1.037 times more likely to give you a high GPA than, I don't know. It's like that.
It's that I don't know part that we need to get figured out.
Yeah.
You were dead on till then. How do regression coefficients always work? It's the change in the y variable per unit change in the x variable. So everything he just said, for a 1 unit increase in your high school English score, your odds of having a high GPA go up by, or I should say the way you said, are 1.03 times higher. Your odds are 1.03 times higher than somebody who has a high school English score 1 unit less than you. There it is. Right? So 1 unit change. It doesn't seem like it's a big number. Is it statistically significant?
No.
No. You can look at the p-value here to decide that, or you can look at the confidence interval. What do you notice about the confidence interval?
One's included.
1 is included. It's not 0 anymore that we look for in there. It's 1 for the odds ratio. So 1 is included there. What about the next one for high school science?
One's still included.
1 is included, but just barely. Look at the p-value. 0.05, bigger than 0.05, but just barely. Right? So there's a 1-to-1 correspondence between this thing containing 1 and the p-value. As soon as the confidence interval shrinks just enough to get on the other side of 1, this would shrink just enough to get on the other side of 0.05.
So would you say it's significant?
Yeah, in a practical sense, I would say, yeah, there's definitely something going on with high school science. And I would probably say, it's not statistically significant at a strict 0.05 level, but it's, come on, we're practical people. There's definitely something going on there.
Because if you remove English, you may see it change.
Yeah. That's
Yeah, that's true. If I remove the English, then it could go up or down a little bit. But,
We try
It
that.
just comes down to
We're done.
English not mattering.
I would try it, but we'll probably run out of time before we get there. This little graph I kind of like. These are graphs of the odds ratios with the confidence intervals. So it's just a visual depiction of what we were just looking at. So here's the number 1. Vertical line. If the confidence interval overlaps that line, then you do not have a statistically significant difference. Look at this one.
It's right on.
It is right on that thing. 0.999. Right? So borderline significance. Okay, now the thing I'm trying to get to here Ooh, I am looking at that. I don't know what that was. Actually, I do. It was a rock curve, but I'm not going to go into it. I want to get down to the output that shows predicted value. Okay? So it took me a while to figure this out, but this is the original data in the columns over to high GPA. And then IP0 and IP, these are predicted probabilities for having a low GPA or a high GPA, right? So now, where did those numbers come from? Let me get a regular marker and go over here. Let's talk about this first person. They have all 10s. Wow. On a 10-point scale, they had all 10s. I'd say there's a really high probability they would have a high GPA. But it's predicting only a 0.62. Let's tell me maybe my model's not that great. But they had, did they have a high GPA?
Yes.
Yes, they did. They had 3.32. The model, log odds, is, I have to go back to the regression output. With the parameter estimates. So read those to me. Negative 6.0528
and 0.036.
Okay, is it positive?
Yes.
Plus 0.0.
361 plus 0.2.
Okay, but that's times high school English, right?
Plus
And plus
0.2489 HSS plus 0.3710 HSN.
okay. Now that first person had all 10s. And that's just pure luck that they had all 10s because it makes this calculation easy. Get your calculators and do this. Plug in 10 for each of those scores and predict for this person. Okay, read it louder.
0.5072.
Okay? Yep. And that doesn't match the 0.62 we saw a minute ago,
E raised to
but that's log odds. So I got to get the probability out of log odds. So how do I get out of log? E to that power. So odds are equal to E to the 0.5072. So what's that?
1.6606.
6606. Now, how do you get from odds to probability?
odds divided by 1 plus.
That's right.
Plus odds.
So the probability of y equal 1. Right, I've been suppressing writing that, but y being the response variable, high GPA. Right? So probability is odds over 1 plus odds. And that's just back solving the definition of odds. So that's 1.6606 divided by 2.6606. I went ahead and did the math in my head on the bottom. Impressive, wasn't it?
So good. 0.6241.
0.6241. Okay, now let's go back and check this. It doesn't want to slide for me. Yeah, now I got two happy. There. 0.62404. So within round off there, that's what they're getting. Okay? All right. I'm out of time, but your homework over this is actually going to be your second project. We're going to do a project starting on Wednesday. That'll be just like the first one, only it's a logistic regression problem. And I will send out by email the paper that you need to read You don't have to read it word for word, but get through the paper so you understand it with the list of questions. I'll have that for you to bring to class Wednesday, and I'll assign the first so many questions for you to have done before you get to class. Then the rest you'll do as a group, or groups. All right? We'll see you then.
When will we know our group?